The next definition is a wide sense the next one is a wide sense or weakly stationary, or is another word, covariance stationary process. When we say the given stochastic process is going to be a wide sense or weakly stationary or covariance stationary, if it is going to satisfy the following properties, following conditions: mean function, that is m of t, is independent of t. The second condition, the second order moment is going to be finite. Basically, the stochastic process is going to be a second order, moments are going to be finite. Third condition, if you find the covariance function c of s comma t, that is a function only on the time difference t minus s for all t comma s. If you find the covariance function for any two random variables x of s and x of t, then that is always going to be a function of the only the difference t minus s, not the actual t or actual s. That is, in words, in mathematically, you can write c of s comma t, that is going to be a function of t minus s in absolute. If this three property is going to be satisfied by any stochastic process, then we say that stochastic process is going to be a wide sense or weakly stationary or covariance stationary. This is entirely different from the Stickson stationary. The Stickson stationary, you are finding the joint distribution of n random variables, then find the joint distribution of n random variables shifted by h, and for all h greater than 0 and for all n, if that property is satisfied, then we say that is a Stickson stationary process. Whereas here we check the mean function is going to be independent of t, and the second order moment is going to be a finite value, and the covariance function is going to be a function of only the difference of t minus s. Therefore, any stochastic process satisfying the Stickson stationary process, Stickson stationary property, that does not imply the wide sense stationary property, as well as the wide sense stationary process need not be satisfied all the Stickson's property. Therefore, you cannot imply one stationary process that does not imply the wide sense, and the wide sense stationary process that does not imply the Stickson's stationary process. So, in the Stickson's process, what we are saying is, it is a stochastic process whose joint distribution does not change when shift in time or space. As a result, the parameters such as the mean and variance, if they exist, also do not change over the time or position for the Stickson's stationary process. Now, I am going to give few examples for the stationary process. Maybe it could be a Stickson stationary process, or it could be a wide sense stationary process. The first example, let xi is going to be a IID random variables, independent identically distributed random variable, and assume that each one is going to be Bernoulli distributed random variable with the parameter p. In notation, it is a binomial distribution with the parameters 1 and p, that is same as each xi's are Bernoulli distributed random variables with the parameter p. Now I am creating a stochastic process with those such IID random variable in which each random variable is a Bernoulli distributed random variable. Therefore, this is going to be a stochastic process. Now you can verify whether it is going to be a stick sense stationary process or a wide sense stationary process. The assumption is all the random variables are mutually independent and each random variable is identically distributed, which is Bernoulli distributed. So, this is just for example sake we have taken, and if you find out the mean function for each random variable, that is going to be expectation of xi, and that is going to be the mean of Bernoulli distribution is going to be p, which is independent of I. The second condition, if you find out what is the second order moment of the second order moment is going to be 1 square into p and 0 into 1 minus p. So, therefore, that is also going to be p. So, if you find out c of some I comma j, instead of s comma t you have I comma j, that is nothing but expectation of x of I x of j minus expectation of x of I expectation of x of j. If you find out this quantity, this is nothing but xi and xj, and since they are independent random variable, therefore expectation of xi into xj is nothing but the expectation of xi into expectation of xj, and that is same as this one. Therefore, this is going to be 0 for all I is not equal to j. For I is equal to j, that is nothing but expectation of xi square minus expectation of xi whole square, that is nothing but the variance, and the variance of the random variable Bernoulli distribution, that is going to be npq. Therefore, that is going to be p into 1 minus p for I is equal to j. And this values is independent of this values is going to be a function of I minus j, you can make out. Therefore, since these all three properties of the weakly stationary property or wide sense stationary property is satisfied, therefore, this is going to be a wide sense stationary process. In fact, even if the random variables are simply IIDs, then too we can check that the process is wide sense stationary. For illustration purpose, we have discussed Bernoulli process. More examples on continuous time stochastic processes are discussed in the problem sheet. Now we can cross check whether this is going to be a stick sense stationary process also. If you find out the joint distribution of suppose you take few random variables x of I1, x of I2, x of I3, x of I n. So this is the n such random variable, and each random variables are Bernoulli distributed with the parameter p, and all are independent. Therefore, the joint distribution is going to be the product of individual distribution. And if you shift this I1 with some number h, and x of I2 plus h, and x of I3 plus h, and so on, x of In plus h. You shift those random variable with the h. If you find out the joint distribution, and since each one is a independent random variable, therefore the joint distribution by shifted by h, that is also going to be the product of those n random variables product. Therefore the distributions are again going to be identical, because each random variable is identical as well as mutually independent. Therefore the joint distribution is going to be product, and all are going to be identical. Therefore it is going to be power n of the distribution. So this is going to be satisfy the Stickson's property, that is the joint distribution of this random variable and joint distribution of this random variable are going to be same for all h as well as for all n also. Since it is satisfied for all h greater than 0 and for all any integer n, therefore this is going to be the same collection of random variables. The stochastic process is going to be a Stickson's stationary process. So this is the cooked up example in which this stochastic process is going to be a Stickson's stationary process as well as a Whiteson's stationary process. But there are many situations in which stochastic process may be a Stickson's, not a Whiteson's, and some stochastic process may be a Whiteson's stationary process, not the Stickson's stationary process. And how this particular stochastic process become a Stickson's and a Whiteson's, because of each random variable is mutually independent as well as identical. Therefore it is going to be a Stickson's stationary process as well as the Whiteson's stationary process.